Hello, welcome to the fourth lecture on monitors. In this lecture, we will explore several issues that may not be directly related to programming. In the first lecture, we discussed the concept of monitors and computation variables. The second lecture presents to you several examples. The third lecture, the previous one, examined a few extensions. Now, it's the conclusion of our general discussion on monitor. The first topics to be discussed would be the equivalence between semaphores and monitors. What does that mean by semaphore and monitor equivalence? In terms of expressive power, semaphores and monitors are equivalent. It means a semaphore can easily be implemented with a monitor. Conversely, a monitor and its condition variable can also be implemented with multiple semaphores, although this is a bit tedious. Therefore, what semaphores can do can also be done with monitors. On the other hand, what monitors can do can also be done by the use of semaphores, because one may be implemented by the other. Some systems may not have semaphores, but they may have monitor. So if you love to use semaphores, you could simply implement semaphores using monitors. On the other hand, some systems only support monitors, only support semaphores, and you could certainly implement monitors by the use of multiple semaphores. So let's first try to do the following. Let's use semaphore. Let's implement semaphore using a monitor. Now look at this one. Always remember we use Hoare monitor. So we define a monitor we call the Hoare semaphore. Recall the definition of a semaphore. We need a counter initially with 0. And we need to have something to block the callers. So we use a condition variable. And we have two functions, P and V. P means wait, V means signal. I'm sure you still remember P is the first letter of an equivalent meaning of wait in Dutch. Dijkstra use P for wait, V for signal. So let's take a look at the wait method. For the wait method, first thing first, we subtract 1 from the counter. If the counter is less than 0, then we wait on the condition variable. And if the counter is not less than 0, we simply return. For the signal or the V methods, we add 1 to the counter and then immediately signal the condition C. In the semaphore definition here, we have an if statement. If count is less than or equal to 0, then we signal. Otherwise, we go away. So please study this version, which implements a semaphore by the use of a Hoare monitor. So please pause if it is needed before you continue. Obviously, the P method, that's the wait, implemented the semaphore wait correctly. But how about V? Without that if statement, does this method work? Yes, of course. Let's remember, in a Hoare or in a monitor, when we signal a condition variable and there's no waiting thread there, then the signal is lost. And if there are waiting threads on that condition variable, one of them will be released. So the correctness of P is no doubt. Now the correctness of V is based on what I said. A signal is lost as if it never happened if there's no one waiting. So let's take a look at the value of counter. F adding 1 to count. If the new value is less than or equal to 0, then we signal one of them will go. Remember, the value of count at this moment, the absolute value of count indicates how many threads are waiting on that semaphore. Now, if the value of count, new value of count is not less than or equal to 0, in the semaphore definition, we do not signal. But here we simply signal. Now, because there's no one waiting there, the signal is lost. Therefore, this is a correct implementation of a semaphore using a Hoare type monitor. Hope you studied it. I am sure in my experience throughout the years, everyone knows this easily. Now, let's take a look at the same implementation. What if the monitor we're going to use is a Mesa type? Does it work? Now, remember this. In a Hoare type monitor, the signaling thread yields the monitor to the released thread. And the signaling thread would wait elsewhere, outside of the monitor. And the monitor is given to the released one. On the other hand, with a Mesa type monitor, the signaling thread continues, but the released one will be pushed outside and become an inactive or re-entry thread. So please pause and investigate my question. Does it work? Please pause. Unfortunately, this implementation, even though it is correct under the Hoare type monitor, it is not correct under the Mesa monitor. Let's go through it. Suppose we have 3 threads involved, T1, T2, T3, and this is a counter. I have some comments here, okay? The problem is a correct signal fails to release a waiting thread properly. Let's see why. Now, T1, subtract 1 from counter. Look at here. In a Mesa monitor, we use while statement rather than if. So currently, after subtracting 1 from the counter, of course, this while statement will see that the new value of count is less than 0, so T1 waits. So T1 blocks. And then T2 comes in. T2 add 1 to count, making the new value of count 0. Right after that, T2 signals condition variable, and the T1 is released because this is a Mesa monitor. T1 is released does not mean T1 could get the monitor. So the signaling thread, which is T2, continues, eventually exits. So what if at this moment, T3 calls P? So at this moment, we have one entry thread, and which is T3, and one inactive or re-entry thread, T1. So what if the monitor mechanism chooses T3 to get into the monitor? So T3 subtract 1 from the counter, making the new value -1, and T3 is here checking the value of count, which is negative, so T3 waits. Now at this moment, the monitor becomes empty. The monitor mechanism is able to release T1 so that T1 can come in. Now remember that the counter value has been reduced to a negative value. So when T1 comes in, T1 will seize that, the counter value being negative, and T1 waits again. So T1 and T3 are both blocked. This is definitely incorrect. This provides you with an example, showing to you that if you solve the problem based on a Hoare monitor, your solution may not work well under a Mesa monitor. We have seen this with the producer-consumer problem. So hopefully you understand this, and if you need more time, don't worry, just pause. Now, the opposite is more complex. Here, we try to implement a Hoare monitor by the use of multiple semaphores. Recall that the monitor boundary creates a natural mutual exclusion. So to simulate this mutual exclusion, we did a mutex lock, whether it is lock or a semaphore, depending on whether your system supports mutex lock or not. So let's call this mutex lock mutex. Now, in a Hoare monitor, the signaling thread uses the monitor to the released one, and then wait somewhere because the signaling thread becomes inactive. So we need a semaphore. Let me call it suspended. The semaphore suspended simply blocks those threads that use the monitor to the released ones. So actually suspended, semaphore suspended would block all the signaling threads. Initialized value would be 0. So suspended is used for blocking the signaling threads. So thread waiting on suspended or inactive or re-entry ones. We need a suspend count to count how many processes suspend on semaphore suspended. We need to know how many guys are waiting on suspended. So here is a implementation for each monitor procedure. For each monitor procedure, the first thing to do is wait on the mutex lock. So after successfully get the mutex, the caller of this monitor procedure is the only one executing in the monitor due to this mutex. Now, upon exit, the caller check to see are there any suspended threads, or in other words, are there any inactive ones? If there are, let one go. And if there are no suspended or inactive thread, we simply release the mutex. Now keep a very important thing in mind. The caller of this monitor procedure successfully enters the monitor by acquiring the mutex lock. Now, upon exit, if this caller sees that there are inactive ones, this caller releases an inactive thread and exits without actually signal this mutex. So the released one, the one was inactive for reentry, receive this mutex from the exiting caller. So in other words, we have a implicit cascading release here. I am here. Now I find out you are inactive waiting somewhere. So I signal you, allowing you to go, and then I exit. And you get the baton. So here we have a passing the baton pattern here. Then let's take a look at how to implement condition variable. Because each condition variable CV has a waiting list to block those who called CV.wait. Therefore, we need a semaphore to simulate this waiting list. And of course, we need to have a counter to count how many threads are waiting on this condition variable. Initial value, 0, of course. Now, for each call to CV.wait, as we mentioned multiple times, any thread that calls wait must wait, no question asked. So the caller to CV.wait add 1 to the CV counter and check to see if there are inactive ones. If there are, give the baton to the inactive one. Why? Because if a thread that can call CV.wait, it means that thread is already in the monitor. As a result, the caller to CV.wait must have the baton. That is the mutex. Therefore, after adding 1 to the condition variable count and checking to see always we have some inactive thread there, so we release 1. And the release one gets a baton that represents the mutex. And if there are no inactive thread, then this caller releases the mutex and immediately wait on the semaphore. After it is released from the semaphore, subtract 1 from it and get out. So let me quickly go through it. A thread that can call CV.wait, it means that thread is executing in a monitor, which also means that thread has the mutex or the baton. So this thread calls CV.wait, it must wait. So add 1 to the condition count. And before it waits here, it checks to see, are there any inactive one? If there are, release 1. The release 1 would get a baton. If there are no inactive one, then I simply release the baton for the next one to coming in, then block myself. Sometime later, when I am released by a CV.signal, subtract 1 from the counter, indicating 1 less thread waiting on the waiting list of this condition variable. So hopefully you will study it carefully before moving on to CV.signal. So here is the implementation of CV.signal. Let's recall what a condition signal will be doing. One, if there are someone waiting on the condition, release one of them and yield the monitor to the released one. Then, if there's no one waiting, the signal is simply lost. So here, always remember, we have the yielding the monitor from the signaling thread to the release thread. So when a thread called CV.signal, check to see are there any waiting. If there's no one waiting, we just get out, no action. If there are someone waiting, why we add 1 to the suspend count? Because this guy will block itself so that the monitor would be yielded to the released one. So if there are someone waiting, then we add 1 to the suspended count, signal the condition variable semaphore, immediately block myself. So sometime later, when I am released from the suspended, that converting my status from inactive to active, then subtract 1 from the suspended count. So let me quickly go through the CV.signal. Always remember, CV.signal does the following. 1, if someone is waiting on that condition variable, release 1. After releasing that one, the caller blocked itself, becoming inactive. And the release one gets the monitor and continue. So the caller check to see, there anyone waiting on the condition variable? If there are, then I'm going to block myself, becoming inactive, at 1 to the counter, and release a thread that is waiting on the condition, and then block myself. This suspended dot wait simply simulates the signaling thread, yield the monitor to the released one. When this thread is released by someone, so the suspended count is subtracted by 1 and gets out. On the other hand, if the condition variable count is not greater than 0, which means no one is waiting, then we do nothing and exit. So this simulates the condition variable signal. So if you want, feel free to pause before we continue. Now we have done simulation of Hoare monitor using semaphores. But how about simulating a Mesa monitor? It's certainly possible to do that because the Hoare monitors is more complex than the Mesa type. So please think it over and do it as an exercise. But I do want to ask you a question. In our implementation of the Hoare monitor, we have a suspended count and suspend semaphore. Whenever we need to release a thread, we are in favor of those threads waiting on the suspended semaphore. Those threads are inactive one. And if there are no inactive one, then we release the button, that's mutex, for the next one to come in. So in other words, in terms of picking a thread to enter the monitor, the inactive or re-entry thread have higher priority than the entering ones. So my question is, what if there's no such requirements? In other words, when a thread becomes inactive re-entry, then it is pushed outside of the monitor and wait alongside the entering threads. Of course, by removing this priority requirement, the implementation will be easier. So think this over, and hopefully you can modify our implementation to achieve this goal. Our next set of discussion will be some comparisons. We compare semaphore against condition variable, also compare semaphores against monitors. So the first comparison is the Hoare type versus Mesa type. You know it well because we have repeated this discussion multiple times. So let's focus on these three. When a signal occurs, a Hoare type monitor would require two context switches. Why two? One switching the signaling process out, and the other switching the released in. Suppose a signaling thread signals a condition variable. That thread must be out. That is suspended. We need one context switch to do that. And then a thread is released from the condition variable. We need another context switch so that that released thread will be able to run or switched in. So we need two context switches. However, a Mesa type monitor only needs one. This is because under the Mesa type monitor, the signaling thread simply remove the released thread from the condition variable and move it out. And then inside the monitor, the signal thread continues. So we don't need a switched out context switch in order to switch the signaling thread out. We only need one context switch to switch the released one from inactive back to running. And this is why Hoare type is more time consuming in terms of doing the number of context switches. Now, for running thread, we have thread scheduling. Under the Hoare type monitor, this thread scheduling has to be extremely reliable because right after signaling thread signals and a released one will run immediately. In other words, you may think this way. The signaling thread has the button of the monitor. And the signaling thread hands the button directly to the released one. This has to be done exactly like what we said. But under the Mesa monitor, there's no such requirement. We simply release a thread and push it outside of the monitor. The signaling thread continues. So this thread scheduling issue won't happen if we run a Mesa monitor. On the other hand, with Mesa type monitor, as you remember, we normally do not use a if statement to check whether the condition is there or not. Instead, we use a while statement, repeatedly checking whether the event I am waiting for has happened or not. So in this case, the burden of inefficiency moves to the user's program. So the user must write his or her program very carefully so that the number of checking could be reduced. However, incorrect signal will do less harm because every thread checks its own condition. So it's always pros and cons. Now, let's compare semaphores against monitors. I use a table. This column has a list of semaphores, the characteristic of semaphores. And this column is for monitor. Now, let's read it row by row. Semaphores can be used anywhere, but should not be used in a monitor. We will explain it later. But as smart as you are, you probably already figured out why. For monitor, can only be accessed with monitor procedure calls. Now, there is a consequence. Many people believe semaphores can be more efficient than than monitors. They have their point well taken. Semaphores, as long as you want to use it, you just put the weight and the signal here and there. That is it. But for monitor, everything you want to control must be inside the monitor. And if the monitor has so many shared things, so threads would go in and go out of the monitor so frequently, efficiency could be a bit lower than the use of semaphore. Now let's look at the second row. When you use semaphore to protect something, protect some data, it's very hard to see the data you want to protect and the semaphore that protects this data. I'm sure if you write program number 4, you know why. Okay, so the programmer must make a connection. So the connection is in the mind of a programmer. If someone is going to read your program, that someone may feel rather difficult to find the connection between the data and the semaphore that used to protect the data. On the other hand, with monitors, the data and access procedures are all in the same place. But as I mentioned earlier, you need to go in and out of the monitor so many times. Efficiency can be lower. Now, you probably have already felt this way. Semaphores are low-level assembly language like instructions. So each semaphore, within each semaphore signal are just 2 instructions. On the other hand, monitors are well-structured, higher-level language construct. You put everything under its umbrella. Now, because there's no connection between the data and the semaphore that used to protect it, and semaphore can scatter. The use of semaphore can be scattered all over the places. So it's not easy to use and prone to bugs. On the other hand, because the monitor has everything under the single umbrella, so ease of use and good protection of vital data. So this is a comparison between semaphores and the monitors. The next comparison we want to do is semaphores versus condition variables. Again, semaphores can be used anywhere, but should not be used in monitor. We'll explain that. Condition variable can only be used in monitors. Remember why. A thread can do a condition weight or condition signal must have the button that represent the mutual exclusion of that monitor. For semaphore wait, you call semaphore wait, it does not always block its caller. For condition variable, you call condition wait, you are always blocked. Now for the signal pass, when you call the semaphore signal, you either releases a thread or just increases the semaphore counter. Of course, whether you release a thread or not, the semaphore counter is always increased by 1. But there is an additional effect. If the new counter value is less than or 0, a thread is released. Now, for condition variable, a signal either releases a thread or the signal is lost as if it never occurs. The reason for this is condition variable is memoryless. It does not memorize how many threads are waiting there. And finally, when you call the semaphore signal, this semaphore signal releases a thread, and the caller and the released one both continue. In other words, if you call the semaphore signal and there are waiting threads there, so one of them would allow you to go, and the caller would also continue. But for condition variable, because you can only call condition signal inside a monitor, which means you are in the monitor and you are the only one in the monitor. If you call condition signal and someone is there waiting, then one of them will be released. However, either the caller or the signaling thread or the release thread can continue. It cannot be both. Under the Hoare monitor type, the signaling thread yields the monitor to the released one. Under the Mesa type, the signaling thread continues, and the released one will be pushed outside, becoming inactive. Hopefully, these 3 comparisons can help you understand the differences between semaphores and the conditions, and the difference between Hoare monitor and the Mesa monitor. And finally, I have 3 remarks. Remark 1, it is suggested that a signal should be the last executed statement before exiting a monitor procedure. We have seen this in many examples. What does that mean? It means, suppose in a monitor procedure, I call the monitor procedure and do something there. And then before I exit, the statement to be executed is a condition variable signal. That is the last one. Why? Whether this monitor is a Hoare type or a Mesa type, the difference between these 2 does not matter. For Hoare type, finally I signals. I am just waiting there as an inactive thread. Finally, when I become active, I'm gone. For the Mesa type, after released a thread, I'm gone. So do you see? So the effect of the signal is the same. If this is Hoare type, the signaling thread will not do anything, even though it is inactive. If this is a Mesa type, the signaling thread will exit immediately. Therefore, this is a safer approach. The second reminder is this. Why is using semaphores in a monitor a bad idea? At least it's not a good idea. Suppose a thread T is executing in monitor A. So monitor A is owned or occupied by thread T because T has the baton. So what if thread T calls a semaphore weighted monitor A and is blocked? So T is blocked by a semaphore inside monitor A. Because T is executing in monitor A, it has the baton. That's the mutex for monitor A. Now, if T is blocked in monitor A, T's baton is never released. So until T is signaled by a semaphore signal, returns to the monitor, and eventually exit, T always has the baton. If T has the baton and wait on a semaphore wait, then nobody can enter the monitor. So using semaphores in a monitor is not a good idea. Most systems simply refuse to allow you to declare a semaphore inside the monitor because you can use condition variable. So by the same idea, you should be able to understand this fairly easily. In most cases, a program only uses one monitor. But what if you use two monitors, A and B? They may be independent, or monitor B is nested inside monitor A. Whatever it is, calling a monitor procedure in another monitor from this monitor is a bad idea. That is, I am in monitor A. I try to call a procedure in monitor B. This is a bad idea. If a thread T is executing in monitor A is occupied by thread T that is owned by thread T. Now, if T successfully calls another monitor B, running in monitor B, keep this in mind, T still has its baton for monitor A. Actually, T now has two batons, one for monitor A, one for monitor B. While T is executing in monitor B, monitor A cannot be used because the mutex or the baton is owned by T, who is now running in monitor B. What's worse, if T is blocked by a condition wait. So T does not own the baton of monitor B, but T still owns the baton in monitor A. So until T is released from a condition variable in monitor B and returns to monitor A and exit. So isn't this a very bad idea? So some monitor implementation would do this as long as the monitor mechanism detects that T now leaves monitor A and enters monitor B, T automatically gives up his baton for monitor A. But that would make monitor implementation rather complex. So keep this in mind. Even though you have multiple monitors in your program, try not to do this nest or cross monitor calls. So this ends lecture 4. The next lecture is going to be a short one. We explain how to use monitors under thread mentor. So let me stop here. See you next time. Goodbye.